Hi everyone, welcome to my channel. Today's video will be a beginner friendly NLP video. So if you haven't done anything related to NLP earlier, then in this video you will see how to take a text data and fit it to a machine learning model. We will see a two different feature engineering technique in NLP, nothing but converting your features or sorry, converting your text into the numerical representation, and that's what we're going to see. So we will be using a scikit-learn library and the pandas library. That is the reason I said it is very beginner friendly video. So the first thing we will do is to import the necessary thing. So we require NumPy, pandas, and from the scikit-learn we require two things. One is the count vectorizer, the other is the TF-IDF vectorizer. We will talk about them once we reach to that particular point. I think we don't need this pipeline. We need a metrics, and we also need a spacey library for tokenization purpose. So let me import this thing. And then I'm loading one data set, which is the same data set that I almost use in all the videos related to the toxic comment data set that I took it from the Kaggle. The reason is that I don't want to much focus on data set, rather focus on the particular technique that we use in that particular video. So you could see we have a simple data set, and it is a small data set that I choose. Just I think it has just 1,000 or 500 records where you have a comment which is a text, and then we identify or there is a data associated with saying that whether that particular comment was a toxic or not, right? And then we will load spacey. So for spacey we have to use one of the spacey model. So here we are using the English small model that spacey offers. So let me load that particular model. And once I load that model, I am just taking some stop words from the spacey. The stop words in the context of NLP is nothing but having some words which almost occur everywhere and they don't carry much meaning. So if I want to decide whether particular comment is, let's say, toxic or not, these stop words might not have anything to offer because they might have occurred in almost all the examples what we have, right? So we want to remove those stop words when we do let's say text preprocessing, so that it will reduce our feature vector. Other thing is that we can also get punctuations, so we can get rid of those punctuation also during our preprocessing. So what I did, I created one a function. I call it like spacey tokenizer. What it does, it just take a sentence. You can think of it takes a text, then it passes the text through the NLP function. Now here NLP is nothing but our spacey model. So if you haven't familiar with spacey, I would encourage you to go and see the spacey is one of the popular library that we use for the NLP, text pre-processing kind of thing, and you could go and look at what are the different model space he has, right? And for each language we have models. So if I click on English, then we have small, medium, large, and even this is the transformer model. So in the current video I just loaded this small model, which is small in the size, also in terms of accuracy also. I think it is just a 12 MB model. So I have loaded that model, and then once I pass through this particular text through the spacey model, what it does actually, it gives tokens to us. So token, you can think of a word or any symbol in English language, you can think of as a token. So what we do, once we get that list of tokens in this spacey context, we call it as a doc object, and we can iterate through the doc object. So this is what we are doing here. So for word in that particular doc, we first do one thing. We calculate the lemma. Lemma is nothing but the root word of that particular thing. So once I run for this particular example, you will understand what exactly I mean. Okay. So the first thing we do, we calculate the lemma, which is the root word for that particular English word, and then we make it lowercase, and then we strip any space it has, let's say left or right, any spaces there. And finally, I get the tokens with their root forms. And the next thing I want is, if my token, nothing but that particular word, if it is one of the stop words or anything related to the punctuation, then I don't want to take it. So that is what I have done here, right? So if you look at what's happening, for word inside my tokens, I check, does this word should not be the word not in stop words and the word not in punctuation. If that is the case, then and then we are taking that word and I'm returning the tokens. So let's run this thing for one particular example so that you get an idea what I'm talking about. So if you see, we are passing a sentence, I am eating apple, and let's say I just put randomly a question mark there. what happens, this particular sentence will go through this particular NLP object, which is nothing but our spacey model, and get converted into this doc object. And the doc, if I print the doc object, I think I already print here, is nothing, it looks same. So if I run this thing, you will see this is what the doc object it printed. It looks same, but if you look at its type, it is different. So let me print the type of the doc. And you will see this thing, right? So even the doc looks same as what I pass as a sentence here, but it is a different type of the spacey object. That is the reason we are iterating through this particular, let me print my token also so that you get the better idea what's happening here, right? So you see what happens. First we just printed our doc, then this is the type of the doc, and then finally we printed the tokens that we got from this spacey, which is nothing but this step, my tokens, right? All the tokens in their lemma form, that is the original form. So if you look at, we have passed eating, but that eating got converted into the it, that is its the lemma or root form, right? And then finally what happened in this particular step, we remove certain words. So we got rid of this word I am, because they are kind of a stop words and not adding any value. That is the reason you see only two words remaining at the end. So more of like a text pre-processing, cleaning, getting rid of certain words that we want, right? And you could add many more steps. I just put two three steps so that you get an idea what do you mean by tokenizing text, or how to clean particular text. Now, this particular tokenizer we can use in the future steps. So while processing our comments, that is the purpose of that particular tokenizer. Now, here is the thing. Now, this is so we know that in machine learning, we can't pass this text directly to a machine learning model. It required that text to be converted into the numbers. Then, whole natural language processing is all about how do we convert this particular text, what you see here, into the numerical representation, right? And each of that technique has its pros and cons. So today we will see a count vectorizer technique and the TF-IDF technique, and we will see what is the difference between them. I won't go much into the theory, but I will try to give you an intuition or idea what's exactly happening. So let's look at what is the count vectorizer, and we will see how does it represent any particular sentence. So let's do one thing. So we have imported already the count vectorizer on the top from the scikit-learn feature extraction, and then we are getting a tokenizer object to it. So if I go to the count vectorizer, this is the sklearn count vectorizer, and if you could see what are different parameter it has, one of the parameters it has a tokenizer. So this is the function that we can pass. Actually, if you don't pass, it will use its default tokenizer. So we can pass a function here as a tokenizer, which actually decide how do we want to process our text and how do we want to convert our text into the tokens. And that is what I shown you earlier. So we want to pass this function as a tokenizer. So what here? So we pass tokenizer is our spacey function. So what will happen? Every time our comment goes through the tokenizer, it will pass that comment through our function, and it will get rid of those particular stop words, punctuation, and convert into the root form. That is the reason I put tokenizer is equal to our spacey tokenizer. So here we are declaring it tokenizer particular object. Now any scikit-learn has model or this kind of transformer has two things. One is the fit method, other is the transform method. So that's what we're going to use. So this is the combination of fit transform method is nothing but it going to consume our, let's say, data set. Here I have given only two sample examples, and then that count vectorizer will learn something from these two example and convert those two text examples into the numerical representation, and we will see what's happening. So this is an two array to just convert it into the array so that we can see it. I think this print statement is distracting. Let me comment them again so that we don't get distracted by them. And let's run our vectorizer again. Now you see our two examples, two sentences got converted into the numerical representation. Now you might not understand what those particular values mean here, but I will tell you what exactly it means. So as a Name suggests count vectorizer. It counts whether particular word is present in that particular sentence or not. And if it is present, then how many times it presents. And if you wanted to know what are different words it has considered, so we can take our count vectorizer and call its method called get feature names, right? And so if I do this thing, I could see it has considered certain words as a features. Word apple, cricket, eat, and play. So there are four words, unique words it has extracted from our data set. And we got rid of I am these words. Why? Because we are using our own tokenizer to get rid of them. Now next question is, how does this value got represented? So what happens when it calculated the unique words present in our whole data set, not just by single sentence, including all the sentences what we have, or all the, let's say, comments what we will have. Once it found all the unique words in that particular thing, it will assign some index to that particular word. Apple will get some index, cricket will get some index, so that it can think in terms of array. So let me see what is that index. You will see Apple got index 0, right? The cricket word got index 1. So once it got some unique index, what it will do, it can represent this one sentence using a vector of length, this thing, of length, the number of unique words we have. And then in that particular vector, it will mark a position. Let's say, let's take an example. So this particular representation is correspond to this particular sentence. So what it will do, it will take word apple and it will check, because the first index belong to apple, it will check does apple present here. Yes, it is present here. How many times it is present? It presents only one. That is the reason at a place of apple you will see one. It go to the next word cricket and it check. Does cricket present into the first sentence? It not present. That's why the cricket index is 0. Then it will check it. Does it present? Yes, it does present. That's why it make it 1. Similarly, it will do for this particular thing also. This is how we are able to convert our text data into the numerical representation. So each comment, actually we are going to represent by a vector which will indicate whether particular word inside that comment is present or not. This is the technique we call the count vectorizer, right? And you might think that okay, this doesn't sounds good, because the text is not just like whether particular word is present or not, right? The text has certain meaning when you arrange those words in a particular fashion, in a particular sequence, and we are missing this, that meaning we are missing in this particular representation. And that is the drawback of this particular representation, right? And that is the reason we have other forms of representation. Even the latest transformers are nothing but kind of embedding, representing our text into the numerical representation. So now we know already how to convert text into the numerical representation, that we can feed it to the machine learning model. Let's use that technique and train our machine learning model. Okay, so I took our data and comment text, I call it as X. That is the common convention in machine learning. And then toxic, which is our actually label, I call it as a Y label. And then we want to split our data. Then we want to split our data into the training and testing, so that we can train our model on something and test it on some other data. So we are using scikit-learn train test split. We pass our our data set here, and we say that we want to keep 20% of our data set as a test data set. And the stratify is nothing but a parameter which makes sure the balance of, if let's say there is imbalance in the data, and that is there is a high chance that it will be imbalance, like toxic and you know um, untoxic kind of comment, right? So that balance will be maintained. So if there are, let's say, 20% toxic and 80% non-toxic, then even train and test will have that same ratio. That's what it does, the stratify. So let me run this thing. Now we got our train and test data set here. Okay, let me check whether did we, yeah, we got our train and test data set. Now what we will do, we will use a simple classification algorithm called logistic regression. So I just imported logistic regression, created its object. And just like we fitted our sample sentence to that count vectorizer. Now we want to fit our data set to that particular count vectorizer. It is the same way. Ultimately, it is going to take the list of sentences, right? So that we can fit to it. So in the count vectorizer, we fit and transform. So fit and transform, what it does, it takes all the training data, learn from it, and also transform. So it has done both the steps, right? It learned from it. What is that learning? Learning is nothing but this calculating this particular feature names, right? And transform is nothing, converting our text into this particular, let's say, matrix representation, what we have here, right? That's what it does. One thing to be noted here, we fit and transform our train data, and this is what we got our vectorizer, account vectorizer here. But we need to fit and transform again on the x, because whatever the transformation that that we have learned from our training data, we want to use same for the testing data, right? That's what we do, and a lot of people miss this particular point, because we can't combine our training and testing data. Then we are leaking out some of the data inside the training data. We want to make sure that if something can work on our training data, it should also work on testing data. So the transformation, if it is working on our training, it also needs to work on the test data, and that's what we will do here. Now it is actually transforming our data set into that vectorized representation. It taking some time. Let's see. Okay, and then I printed its shape. So since we had 1,000 examples, you could see there are 800 in the training and there are 200 in the testing, because we had a ratio of 20% for the testing. And you see the shape, the size of the each example is actually 5783, and that 5783, it is nothing but the unique words we have in our data set. That is the reason each example is of a length 5783, right? Now since we have our data, if you are curious, we can see this data will be a numerical data or maybe a sparse matrix representation. So this is a sparse metric representation, and that is the reason why we use this two array notion of it. So if I use two array, I'm not sure. Let's see. It will be a very, yeah. So this is how the numerical representation our data has, and you could see it is very sparse. Why sparse? Because we have a unique words in our data set, almost more than 5,000 words, but we know that each comment only going to have maybe, let's say, 20, 50, or 100 words, right? So you will have some value only for those 20, 50, or 100 word location. The all other positions in that particular vector will be the empty, and that is the one of the drawback of the this count vector representation, that even though your text is very small, maybe just 50 word of length, but to represent that 50 word text, you are actually consuming a 5,000 dimensional vector, and that generate this particular sparse matrix. So that is one of the drawback what we have. Let's fit our data, whatever the training vectors what we got created, let's fit to our classifier algorithm, which is nothing but the logistic regression. Okay, and I also printed the some accuracy. So we fitted here, okay, classifier dot fit, and we use that same classifier to predict on our test vectors which are here, right? And then finally, when we got the prediction, we compare our test labels with our predictions and calculate accuracy, precision, and recall score for our algorithm. And we see we got something around 84% of accuracy, around 87% precision, and 81% of the recall. That is the thing we got when we represent our text using the count vectorizer. Now we have other technique also called TF-IDF vectorizer, right? That is the term frequency inverse document frequency. We might want to spend some time here to understand what exactly this thing, and how does it differ from the count vectorizer that we just did, just we use, right? So let me go to here. Like this is one of the Medium article I came across, which explains good way, what is TF-IDF. So TF-IDF stands for term frequency and the inverse document frequency. So this particular term is actually made up of two things, term frequency and the inverse document frequency. So what is term frequency here? So term frequency, here term, first of all, the term is nothing but particular word or token that you see here, right? So in this case, this apple is one of the term present in that particular example. So right. So let's say we want to calculate that term frequency for the apple or the inverse document frequency for the apple, that how will it be, right? So what is term frequency? Term frequency is actually the frequency of word inside that particular document. Okay, so you could now see the term frequency is the something which actually get associated with only that particular document. So if I have a word apple, then it will have some term frequency value for this example and will also have some value for this particular example because it is associated with that particular document. So it is the frequency of that particular word in document. And how do we calculate that thing? Using this thing, we count how many times that particular term occurred in that document and how many words inside that document. So let's take an example of our apple, right? Seems to be apple has occurred only once in this document. And how many words are here? There are four words in that document. So the term frequency of the apple become 1 by 4th. So it becomes the 1 by 4th, which is almost 25, 0.5 or 25%, right? That is the term frequency of apple. Similarly, we can calculate the term frequency of any other word like, cricket or something, right? Let's say here we have I am eating apple, and if you say that I like apple, then what will happen? Term frequency will change because apple has occurred now twice out of all this, right? So instead of become, let's say, 1 by 4, now it will become, how many words are there? 4 and this 3. So it will become 2 by 7 now, term frequency. Because out of 7 words, it has occurred twice. That is the term frequency of that particular word apple. Then what is the inverse document frequency? Now the inverse document frequency is nothing but what it does. Let me see where is the definition. Yeah. So inverse document frequency is depend on the document frequency. Now what is document frequency? Document frequency is that particular term occur in how many other documents, right? So let's go back here and see the word apple. You could see apple has occurred only one document because it is not here. But let's take this top word, I. I has occurred in both the documents. It has occurred here also, it has occurred here also. So document frequency of the I will be 2 because it has occurred in two documents. But whereas the document frequency of the apple will be only 1 because it has occurred in only one document. Now let's see how does it relate to. So inverse document frequency is actually 1 by that particular value. So for this particular I, it will become 1 by that particular document frequency or the not one, sorry, it's the n by document frequency. So if you have, let's say, 10,000 documents and it has occurred, let's say, 10 other document, then value become 10,000 divided by 10. Now you might think like, how does this thing matter, right? Whatever we are doing in the TF-IDF context, how does this is, compared to what we had in count vectorizer? So if you look at the count vectorizer, we are simply counting whether particular word is present or not, or how many times it is present. What TF-IDF trying to do, it is calculating two things, term frequency and the inverse document frequency. But term frequency is the value indicate that how much important that particular word inside that document. Because if Apple is coming two times here, it means definitely Apple has a more importance compared to other words inside this document. So if so doc for this particular word, Apple should get the high term frequency here because it has a high importance. What is inverse document frequency? But what if the word apple also occur in all other document? Then we don't want to give apple more importance because since it is occurring in all the documents or all the text and comment, it doesn't have the differentiating factor to differentiate between the comments, right? That is the reason the stop words will get very low score for the TF-IDF. Why? Because though they will appear in that particular document multiple times, but their document frequency is nothing but how many times they have occurred into the other document, that will be also very much high in the number. So what will happen? Term frequency, let's imagine the worst case, we have 10,000 documents, right? 10,000 documents, and you have a particular word stop word which occurred in all other 10,000 documents. Then this IDF value become 1, right? But let's say this is the word apple, which actually occurred only out of 10,000, only 100 document. Then what will happen? The term frequency, sorry, the inverse document frequency of word apple will become 10,000 divided by, let's say, 100, which is 10. So you see, apple got higher weightage because it has occurred in this document and it is very rare word. So if the word is rare across all the documents, but very much frequently occur in that particular document, then that word will have higher value of TF-IDF, and that is the, you know, advantage, or the, you can think of, that is the something best thing we have over the count vectorizer, where count vectorizer doesn't differentiate whether, though it is saying that this particular word, let's say I occurring here, but it doesn't consider how frequently I across all the documents, because if I is going to occur in every other document, then I don't have any differentiating power. Okay, so that's what TF-IDF does. So if you want to learn more about this particular, theoretic understanding of different techniques like this count vector, TF-IDF, word to vec, I recently came across one of the video that Ramsey has done on his channel. If you can go to this particular channel, and he has explained, how the NLP feature technique has been evolved from, let's say, TF-IDF to different feature engineering technique, right? So you can go and watch for the theoretical understanding. Today we will focus more of, like, having some intuition that how term frequency and inverse document frequency give higher weightage to the words which has, high frequency in particular document but very low frequency across the, or we can see that very low occurrence in the other documents, so we can call those words as the rare words, right? So maybe I'm repeating now same thing. So that is what, the TF-IDF does, and we will see, since TF-IDF is able to get rid of these top words, right? So it will eventually give less weightage to the words which has occurred in all other documents, right? So it should have a better feature representation compared to the count vector, and most of the times we get the better accuracy or whatever metric, right? It is not always the case, it depends on your data set, right? But this is what likely to happen, that we should get the better performance when you use the TF-IDF feature engineering technique. So let's do that thing. Instead of count vectorizer, we will use the TF-IDF vectorizer, right? And then we will do the same procedure. We will calculate our train and test, right, vectors. We will fit to the, again, a logistic regression, and we will do the prediction, and we will see is there any performance difference, what we see. Okay, so let's compare. Do you see any significant difference? So first of all, we see the accuracy has improved. Okay, and we also see the precision has improved significantly, but we see a drop in the recall slightly. So we did improve the accuracy and precision, but there is a slight drop in the recall. But overall, TF-IDF has done better than the, um, what I say, the better than the count vector method. And intuitively, it should definitely do a better. Now, it depends on your business use case whether you value, let's say, precision more over the recall. So, depends on your, depends on your business use case. You're going to maybe fine tune this particular model, change their parameters so that you get the desired output. So, this is what the overall. So, if you have any text data and you want to fit that takes data to a machine learning model, like in our case it was the classification problem, a text classification problem, where we want to see whether the given particular text is, given text is a toxic or not. So we had a two approaches. One is the count vectorizer, the other one was the TF-IDF vectorizer, right? So count vectorizer, we just saw it simply count whether particular word is present or not, and then create that vector representation. We feed it to the machine learning model, and we got some kind of, metric, some accuracy, precision record. Similarly, we with the TF-IDF factorizer, and we saw that the TF-IDF factorizer give high weightage to the words which occur very frequently in a particular document, but they are not occurring that frequently, or they are rare if you compare to all other documents, right? So that was the agenda for the today's video. I hope you at least got some idea. This, you can think of this is like getting started video with the natural language processing. My earlier videos were advanced videos because there I have used transformer, pytorch, and all those kind of things, right? So maybe you can watch this particular video first, and then you can move on to the more complex topics, like doing same things with the transformer models kind of stuff, right? And if you found this video useful, please do subscribe. I create videos related to the natural language processing. Earlier, I have created videos using transformer libraries and sentence transformer. That also you can go and watch. And this is something like a lot of people were, requesting, can you create the beginner video? That is the reason I created this beginner level video. Thank you.